Okay, so this next application of moles is a very important one because it's really going to help you with your first online lab. Okay, now if you remember, we actually completed this lab. We actually did the phosphate lab, which is, you know, the one we're going to do online, so to speak. Okay, I am going to provide you individually with some kind of manufactured data because we didn't really get around to weighing your stuff, right? Okay, so, you know, we'll just pretend that the numbers you have, which I give you, are your actual answers. Okay, now this packet, or this video in fact, is going to be kind of a template to help you with the questions. Okay, because the most important part of this lab is answering the questions, and in a separate video which I'll post, you know, elsewhere in a discussion, we'll actually work together through a couple of sample problems in your lab. Okay, and you'll actually work out the rest of the problems and then, you know, send them to me for grading. Okay, so that's not going to be for a little while. We want to get through this theory first. Okay, so let's talk about it. Now, first, a few important definitions. Okay, well, before we even say that, this is called quantitative stoichiometry. Okay, so basically putting numbers for grams and moles into essentially balanced chemical equations. All right. Now, back in the day when I was in graduate school, I worked with a very well-known professor who, it's not my invention, we'll see it, I really like it, it's called Slides and Ladders. Her name was Eva Rochek, and she was very influential on me, and she showed me the way forward with this for teaching. Okay, so I'm going to show you a different technique in the book. We will show you how they do it in the book as well. If you happen to like that, that's great, but this is a much better way to do it. It's kind of like the difference between directions and a map. Okay, a map is easier to follow than just someone telling you where to go. Okay, so Slides and Ladders, if you like, is like a map way of solving these problems, which, you know, is a nice way to do it. Okay, but back to those definitions. Now, theoretical yield. What we're going to do with this technique, the Slides and Ladders technique, allows you to work out theoretical yield. Now, what is theoretical yield? It's what you should get if everything goes perfect in a reaction. So if you remember your calcium phosphate lab, you made that precipitate, right? Sitting in the fume hood at JJC right now. Okay, you can work out, if everything goes perfect, how much of that stuff you should make, okay, in grams. Please ignore the phone because, you know, I'm at home. Okay, the actual yield is what you actually pull out of the oven. So when you weighed your stuff, should you have done that in lab, you get the actual yield. Okay, so actual is what you actually physically weighed, and theoretical is what you work out that it should weigh, which comes from this theory we're going to discuss in this packet. Okay, now a measure of how good you are, everyone wants 90% or better on a test, right? Well, it kind of works the same with percent yield. Yeah, if you work out, hey, what you got divided by what you should have got times 100, it gives you percent of how good you were. So if you got 9 grams when you should have got 10, that's a 90% yield. That's pretty good, right? If you only got 5 grams when you should have got 10, that's only 50%. Okay, so it's what you got over what you should have got times 100 gives you a percent yield. And in the lab, sorry, in the experiment, when we talk about this later, you're actually going to work out some of these numbers. Okay, now discussion. Are theoretical yields and actual yields ever the same in practice? Can you ever do the perfect experiment? The answer is a big no. Okay, there are two ways this can go. You can either be too high, and some of the data sets you'll see, you'll get too high yield. You say to yourself, well, how can I get 140% if the maximum's 100? Well, it's because it's not just product. If you don't dry it long enough, there's actually still some water in there, so it weighs more than it should. So you can actually get numbers in the 120, 130, maybe 140% range. And should we have done this, you know, for real at school, you would have all got high numbers because the precipitate is really hard to dry. Okay. In industry, they don't have drying problems, so the numbers are always low. Okay, so 90, 95, things like that. Okay, so essentially your goal as an industrial chemist is to get the highest percent yield as possible, the maximum amount as a percent of dry product. Okay, 90% or better is expected in industry, and if you get lower than that, oftentimes you're looking for a new job. Okay, so high would be wet, and low because you have spillages. Okay, so if you think about it, if you do some chemistry, you're transferring chemicals from one container to another along the way. Do you ever pour everything from here to here? No, you lose a little bit. And then the more steps you have in your procedure, the more you collectively would lose, okay? So what people actually do in industry is they actually prepare things with as minimal steps as possible, which is a nice technique, okay? But anyway, you know, you can get lower than 100%, you can get higher than 100%, both are normal errors in this experiment, but never ever expect 100%. Okay, now, my example of slides and ladders features something maybe we're familiar with, right? If you remember this person, you may recognize this person. Okay, so finding theoretical yields using slides and ladders, I call this the Hank Hill example. All right. Now, Hank Hill, if you're a fan of the show, is a purveyor of propane and propane-related accessories. Should I do the impression? Bobby. Kind of trying to. All right. Now, here's the thing. So this is a worked example of a slides and ladders to get theoretical yield. Okay. Now, we're going to burn 5 grams of propane. There's the formula. I'm going to combust it in oxygen, so we're going to burn it. What mass of water is expected to be formed? What mass of CO2 is expected to be formed? So those are theoretical yields. Okay, if you work out the mass of products, that's theoretical yield. Ty, theoretical yield. Ty. Okay, and because we know the relationship, and this is why we did it earlier, the relationship between volume and moles, we can also work out just a quick side calculation using 1 mole is 22.4. What volume is CO2? There's a trick. STP means use the 22.4. So there's a procedure for this, okay, and it's cumulative. So we are going to use things we've done before, okay. So first things first, write a balanced chemical equation, all right, and then 2, set up a grid. Now what I'm going to do, I'm actually going to go straight to the second page here, and I advise you to do the same, okay. So we need a lot of room for this, okay? It's kind of a map, all right? So a balanced chemical equation, let me get this all on the same page here. A balanced chemical equation and a grid. Okay, what does that look like? Okay, so balanced chemical equation, so we're burning propane, C3H8 liquid, okay? With oxygen, O2 gas. And remember, we're going to burn an organic to make carbon dioxide. Combustion of carbon makes carbon dioxide. And combustion of hydrogen makes water. First step is balanced chemical equation, but leave space underneath down here, okay, for work. Okay? 3 carbons, 1 carbon. So we need 3 CO2s. Hopefully you're familiar with this kind of thing now. 8 hydrogens, 2 in there, so we need 4. That means we've locked in 2 3s are 6, plus 4 oxygen, 6 plus 4 is 10, 2 times 5. So there's our balanced chemical equation. That's the first step in calculating theoretical yield, is a balanced chemical equation. Now, if you remember, I showed you earlier my little shortcut, okay? Grams is molecular weight times moles. Molecular weight is grams per mole, and moles is grams divided by molecular weight. We're going to use that triangle to make our conversions really easily. You can do all this with a really long chain conversion. You can. And maybe we'll show you that at the end just to show you it's the same. But this is by far a much easier method. Okay. So what I'm going to do, let's move this up just a little bit. Okay. What I'm going to do is set up a grid. The grid's going to have grams, molecular weight, and moles. Okay, and it's called slides and ladders because each reactant and product has their own little ladder here, if that makes sense. Okay, makes their own little ladder. Okay, and what we're going to do, step 3, let's bring that up just to show you a second. Fill in the grid with as much information as possible from the question, right? So if you read our question, 5 grams of propane is combusted. Well, there's my propane, there's my grams. It's like a game of Battleship, right? So that's the grams of propane box, right? So I'm going to put 5.0 in there. All right. Oxygen, Well, we don't care, to be honest. We'll talk about why later, but this is never going to run out. We're never going to run out of oxygen from the air, so it doesn't affect our calculation, and we'll see why later in the packet. But for now, if it's excess, if there's, it's not going to run out, doesn't worry about it. This here, the grams of product, that's our theoretical yield. That's where we want to go. That's our destination. Theoretical yield, that's our destination. Fair enough. All right. Now, one molecule reacts with 5 to make 3 and 4. But here's the important thing. This is a number ratio, not a gram ratio, right? Okay. So we can't just fill this in right off the bat, okay? We have to work out the number of molecules, or if you like, the number of moles of molecules. So our journey is always going to be down, climb down the ladder. This is called slides and ladders. Slide across, and then climb back up. Slide across, climb back up. Now each one of these is a 2-link in the chain conversion, which we'll do later just to show you it's the same thing. But the map is certainly makes life easier. Okay, so next thing, in order to turn grams to moles to complete the first leg of the journey, hey, moles is grams divided by molecular weight. So if we got these molecular weights, and for completeness we can do them all just for fun, right? These are all from before. Now remember, the definition of molecular weight is grams per 1 mole, not 4, 1. 2 H's and O is 18 grams per mole. CO2, 44 grams per mole. These are all examples from before. Oxygen, we don't need it because it doesn't come to the math, and if you want it for completeness, it's 32, right? Here, well, 3 carbons, 8 hydrogens, 44.11 grams per mole. Okay, so we filled in pretty much as we can from the question, and we made our map, okay? So let's just read it. 5 grams of propane, excess oxygen, what mass of products do you expect? Okay, molecular weight row, because you have the formulas, you can just fill that out. And there's our destinations all plugged in. All right, so reading down, we filled in as much information as we can. Now we're just going to climb down the ladder. All right, we're going to climb down the ladder. Here's the key thing. This is why this triangle is so good. Okay, we want moles, right? Moles is what? Grams divided by molecular weight. So all you do to climb down is divide, right? Divide. So it's grams divided by molecular weight is moles. Okay, this makes life a lot easier. What is 5.00 divided by 44? 0.113, right? Okay, fair enough. Now, this is the fun part. Why is it called slides and ladders? Now, as I mentioned, a gram doesn't react with a gram, right? Why do we balance this? Because one molecule reacts with 5 molecules to make 3 and 4. It's a ratio, ladies and gentlemen. 10 would react with, say it with me, 10 would react with 50, right? To make 30 and 40. 2 would react with 10 to make 6 and 8. It's a mole ratio, right? For every one of these, I react 5 of these to make 3 and 4. That's a ratio. Hey, there's the actual number of moles in the test tube though. There's not 1 mole in the test tube, there's 0.113. All I know is, hey, 1 makes 3. So 0.1 would make 0.3. If I add in all the change there, this is just 3 times bigger, right? You look at this ratio, 1 makes 3, it's 3 times bigger. What's that times 3? 0.339. Nice spot for a pause. What would this be? 1 makes 4, so it's 4 times bigger, right? What's that? 0.452 moles. So we're constructing our grid, right? We're constructing our grid. Fantastic. Now, our destination is here. If you divide to go down, we slid across, what do you think you do to go up if you divide to go down? If you said multiplied, you are 100% right. Grams is what? Molecular weight times moles. Multiply to go up. Okay? So do that. This times this equals this. This times this equals this. Fill in the numbers. What do you get? 14.92 grams, 8.13. Maybe some rounding in there somewhere. So that's your first example of a slides and ladders. Okay, first example of a slides and ladders. All right, just to finish off the question, it does say how many, well, let's just read back, right? Let's go back. What mass and volume of CO2? All right, so we've got the mass of CO2. But what about the volume? Remember, volume CO2, it's going to be like a side calculation. There is no box for volume. Okay, there is no box for volume, but we have got this. We have got the moles of CO2. If you remember your spider diagram, right, what can we do? 0.339 moles at STP, 1 mole is 22.4 litres. What is 0.339 times 24 divided by 1? Survey says 7.54 litres. Okay. So that's your first example of the complete slides and ladders. Now, just to show you that I can do this with a straight chain conversion. This is one link in the chain, this is one link in the chain, this is one link in the chain. Okay, so if I start with 5.00 grams of C3H8, I can turn it into moles, right? I divide to go down, divide by 44.11. That gets me to here. If I press the equals, I get 0.113. Now if I want to slide across, this is interesting, right? 1 mole makes 3 moles. So I'm going to do a weird conversion factor. We just kind of did it intuitively when I talked about the grid, right? But 1 mole of CO2, sorry, 1 mole of C3H8 makes 3 moles of CO2, right? C3H8. That's propane, that's carbon dioxide. So just multiplying by 3, that's this leg right here. Then finally, to climb back up, we're carrying moles of CO2. 1 mole is 44 grams per mole. Climb up, and it equals the answer. Okay, now choose which one you like, right? If you really like the chain conversions, we saw something a little different here where the conversion factor there is 1 mole CO2 equals 3 moles. Sorry, let me do that again. 1 mole C2H8, 1 mole CO2. So it's the same kind of idea. We just link conversion factors together, and each conversion factor link is an arrow here. Okay. If you're doing this for the first time ever, I'd suggest learning the grid method. If you're maybe done this before, maybe in high school or somewhere else, you choose, right? I mean, if you like the grid, fine. If you want to do the chain, that's fine as well. All right. So, group tasks. Practice makes perfect. Okay, so what I want you guys to do is practice with these problems. This is a great spot to pause, all right? And then when we get to the bottom down here, we'll actually go and pull out our labs, and we'll actually use this as a guide to answer those lab questions, okay? So consider this a warm-up for your lab. All right, and the next thing we do together, well, actually we'll finish the packet first, and then I'll put the lab up, okay? So no rush to do the lab. We'll finish this packet, so one more video after this one, and then we'll do the lab, okay? So, first things first, again, feel free to pause, right? And then we can give this a go. All right, so question number 1, carbonate. You have to excuse me while I just flip through my notes here. There. So, question number 1. This is one of my favorite questions to ask because the numbers are nice, okay? So, I'm going to do the grid. follow the rules, right? Let's set up a grid. Then we'll answer the questions. So what mass of dissolved HCl? Interesting. It doesn't matter which ladder you climb up and down. You can figure out any of these. So you can work out mass of products, which is a traditional way to do it, or you can work out how much stuff you use. In our previous example, this was excess. We're never going to run out, right? But here, when we put things in the test tube, we can kind of figure out, well, how much do I need to throw in with this to make it work? Okay, so we're going to react 5 grams of chalk, calcium carbonate, 5 grams, right? We want this one. And it also said, what's the volume of CO2 generated, right? We can't get, well, we could work out the mass, right? And maybe we'll just put everything in for completeness, right? Okay, but our destination is here, because if we want volume of CO2, like we did in the last one, turn moles to volume, okay, with the 22.4 thing. So let's look at this equation first. So let's just, that's like an overview, right? Let's just go through the steps one at a time. So first step is to write a balanced chemical equation, okay? If you can see here, 1 calcium, 1 calcium, 1 hydrogen, 2 hydrogens. 2 chlorines, 2 chlorines, 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 and 1 makes, sorry, 2 and 1 makes 3. It's balanced. So it's actually pretty easy to balance. 1 reacts with 2 to make 1, 1 and 1. Fair enough. Okay, so first step complete, balance the equation. Next step, make a grid, fill in everything you can. Let's just fill in the whole thing just for completeness, okay? I know our destinations are here and here, but let's fill out every single box just to show you how it works, right? So the next thing is, fill out this row, right? Okay, so calcium carbonate, you can add up those parts. The reason I like this is because it's 100 grams per mole, all right? This one here, remember it's for 1 molecule, so 35.45 plus 1, if you check your periodic table, 35.45, that's 36.45 grams per mole. Calcium chloride, we did that one before, that's 111 grams per mole. Carbon dioxide is 44, and water is 18. If you're not remembering how to do this, flip back and look at how we work out molar masses, okay? Remember, it's for 1 molecule, not 2. The 2 comes when we start sliding around, right? But this number is for 1, okay? Divide to go down. What is 5 divided by 100? 0.05, 366, 0.0500, all right. One of these reacts with 2 of those. So 0.05 needs twice as much, 0.100. And then 1 reacts with 2, 0.05 reacts with 0.1 to make 111, or the same number here, 0.05, 0.05, oh, 0.05. There we go. All right. Now, nearly there, right? Okay. Multiply to go up. What is 0.1 times 36? 3.645. So the theoretical yield of HCl is 3.645 grams. Okay, multiply to go up. Multiply to go up here. That's going to be 0.05 times 111, 5.55 grams. This is just for completeness. 0.05 times 44, 2.2 grams. And finally, 0.05 times 18.90 grams. Now, don't forget the conservation of mass law, right? So 5 plus 3 is approximately 8.6, right? 8.6 is the mass of the reactants, right? That should equal the mass of the products. Well, 5.5 plus 2, 7, plus 1 more is 8. So yeah, I mean, you add these up, it's 8 this side approximately and 8 this side. If you work out all the decimals, it's the same. Okay, so mass of reactants equals mass of products. That's always true. Okay, so 3.645 or 3.65 with the sig figs for the mass of HCl. Now real quick, let me do it down here. Volume CO2, well, I've got 0.05 moles times 22.4 litres is 1 mole, which equals 1.12 litres. Okay. Alright, so remember that volume calculation is always on the side. This is a grid with grams, molecular weight and moles. There is no box for volume, but hey, work it out on the side. There you go. Alright. Okay. Next one. Careful, this is kind of a flashback, right? Hopefully it's not traumatic, right? We're talking about the magnesium equation, right? So magnesium, well, let's read it. What mass of magnesium oxide is recovered when 1.6 grams of magnesium is burnt in air? So we're burning in oxygen. What volume of O2 is consumed? So let's do the whole grid again for completeness, right? So magnesium and oxygen makes magnesium oxide. Careful, do you remember? +2, -2, right? And then we've got to balance that thing. If you remember from before, those are the balancing numbers. Flip back, feel free to look at the balancing packet if you need to refresh that. Okay. Grams, molecular weight, moles. Let's read the question. What mass of magnesium oxide? So it's a traditional question. What mass should we get when 1.56 grams of this guy is reacted in air, so that's excess, we're never going to run out of that, over here. Okay, so look at the old periodic table, find out the atomic mass of magnesium. I'm just going to quickly Google it so I don't have the periodic table. Mg, oh, Mg 24.305. 24.305 grams per mole. Oxygen, well, if you wanted it, you could put it in 2/16, 32 grams per mole. Magnesium oxide, 24.3 plus 16 equals 40.3. Remember, it's for one molecule, right? This one and this one. Okay, so we've filled in everything we can. We've got a balanced equation. Now remember the trick. Divide to go down. Okay, so our journey is here to here to here. All right. Okay, remember we always climb down, slides and ladders, climb down, slide across, climb up. Okay. Now, divide to go down. Let's do the math. 1.56 divided by 24.305 equals 0.0642. Okay, moles. That's how many moles 1.56 grams of magnesium actually is. Now here's the thing. 2 makes 2. It's the same number, right? So how do you turn a 2 into a 2? Well, you multiply by 1. It's the same number, right? So 0.0642. Multiply to go up. Times 40.3, 2.59. 2.59 grams is the answer. Okay. For completeness, let's fill out that number. And actually, we do actually need that number because it says what volume of oxygen gas, so we need the moles of oxygen gas. Hey, 2 reacts with 1. How do I turn a 2 into a 1? Well, I divide by 2. So if it's a smaller number in ratio, I'm going to divide 0.0642 divided by 2 is 0.0321. Okay. Then take that on the side. 0.0321 moles of O2 times 22.4 liters for 1 mole equals, what do we get? 0.71 liters. Okay, 6 figs, 0.71 something, right? Okay, hopefully that makes sense, all right? Again, you know, the great thing about these videos is you can kind of pause, rewind, all that good stuff. And also feel free to ask questions in discussion, very important. All right, final one, an easy one to finish. Okay, if we just go back to our definition of what percent yield is is actual, what you got, over theoretical, which is this number right here when we do the slides and ladders,